Mwalimu Teofili Academy reminds you that success is not an overnight process, but consistency. Welcome for today's session.
The second example states that a current of 3.2 ampere is passed through a solution of copper 2 sulfate for 30 minutes. What is the mass of copper deposited at a cathode? You are given the relative atomic mass of copper is 63.5. The relative atomic mass of sulfur is 32. The relative atomic mass of oxygen is 16. Solution. Let us first of all analyze the data which we have. Data given. The data given here, we are given current electricity, current I. The current you are given here is 3.2 ampere. 3.2 ampere. Another data which we have time. 30 minutes. Time. We're given time. Time T is equal to 30 minutes. 30 minutes. When you convert this time into seconds, you are going to have 30 times 60, which will be seconds. Now this will be equal to 1,800 seconds. This is the time which is equivalent to 30 minutes. 1,800 seconds. Now, another data we have here, we have almost relative atomic masses of these various elements: copper, sulfur, and oxygen. Now, what is required here is to calculate the mass of copper deposited. The mass M of copper deposited. Mass M of copper deposited is required. It's not known. Now let us use this data to calculate this mass of copper deposited on the cathode. Which approach are you going to use? Here we may use the approach of firstly balancing the chemical equation. I mean that by considering the reaction which was occurring at cathode. As you know, at cathode, copper is going to be reduced. Now copper will be reduced to copper atom. I have decided to use this of balanced chemical equation because we are not given the electrochemical equivalent of copper directly. So we may use these prevailing data directly without involvement of electrochemical equivalent by using the balanced chemical equation. Now let us balance it. Here, let us consider reaction at cathode. The reaction at cathode will involve the reduction of copper ion into copper metal. Now it will be copper 2 ion. It will gain the electrons equivalent to these ions, I mean 2 electrons, and it will be discharged to copper, which is solid. Now this is in aqueous form. As you can see, this is the balanced equation for this reaction. Now we use the concept of mole concept, especially on the section of stoichiometry. Here, 2 moles of electrons are equivalent with 1 mole of copper solid. So 2 moles of electrons, we say 2 moles of electrons are equivalent to 1 mole of copper metal. Here, these 2 moles of electrons, if you remember, we said that the number of moles of electrons are equivalent to the number of Faradays. So instead of writing 2 moles of electrons, we can also write 2 Faradays. Now we say 2 Faradays are equivalent to 1 mole of copper. So if this is the case, here we are going to convert these Faradays into coulombs so as to be in the position of being able of using the given current and time. As you know, when we take current times time, we get the charge in terms of coulombs. So in order to make it to relate with the standard equation here which we are preparing, let us convert these Faradays into coulombs. You have to know that 1 Faraday is equal to 96,500 coulombs. So here, to convert these 2 Faradays into coulombs, it will be 2 times 96,500 coulombs. So instead of writing 2 Faradays, I can write 2 times 96,500 coulombs. Now 2 times 96,500 coulombs will be equivalent to 1 mole of copper. But also, I am going to convert this 1 mole of copper into mass, as you have to know that what we are looking here, we are required to calculate the mass of copper deposited at cathode. So if we are required to calculate the mass of copper deposited at cathode, it means that even this mole can be compared with the equivalent mass, so as to be in the position of relating the mass obtained with the particular mass which is asked. So here, 1 mole of copper, we are told that 1 mole of copper is equal to 63.5 gram per mole. Now, it is, instead of writing 1 mole, I'm going to write 63.5 gram of copper. So this is the way. Here, this is the data from the standard equation. This is the data from the standard equation. Now from this, let us compare it with the data from the given, let us compare it with the data from the question. From the question, we are given the current of 3.2 ampere and time of 1,800 seconds. So, as I've told you that when we take the product of current and time, we get the charge in terms of coulomb, as we have here. So it means this 3.2 ampere times 3.2 ampere times 1,008 seconds will be equivalent to how much mass, to m, as the mass which is required is not known. So here, this current, when this current is applied within this time, 1,080 seconds, we are going to get the mass m. Mass m of copper will be deposited at cathode, but this mass is not known and is what we are looking for according to the question given. Now, to get this mass, let us cross multiplication. We are going to cross multiplication of these values which we have. After crossing multiplication, here we are going to have 2 times 96,500 coulombs times m this. This answer will be equal to 3.2 times 1,800 times 63.5. Now here, let us use a calculator to multiply these various values. Now we have on the left hand side you have 2 times 96,500. When you multiply it, you get 193,000. This is m. As you have seen, we've got 193,000 m. As you know that m is not known. Now this value will be equal to 3.2 times 1,800 times 63.5. When you multiply this, you get 365,760. Now this is the answer we get on the right hand side. Now after obtaining this, what is next is to divide by 193,000 both sides so as to remain with m. Now how it comes, it will be this way: 193,000 m is equal to 365, 760. So here we are in the position of dividing by 193,000 both sides so as to remain with the m. 193,000 both sides. We divide by 193 both sides so as to remain with the value of m. Now this value will cancel out because they are equal. So on the left hand side we are going to remain with the m. Now our m will be equal to, let us take this over this. Here we are going to have this over 193,000. 193,000. The answer here becomes 1.895. This is the answer. Now you have to remember this is mass, so it is in gram. As all data used in forms of mass, they are in gram. So even the final answer will be the mass which is in gram. Here, when you approximate this value, you're going to have 1.90 gram. So this is the mass of copper which will be deposited at the cathode. Apart from this approach, also we have an alternative. The alternative which can be used here, apart from this, let us have an alternative. An alternative which can be used to solve this question is to use directly the formula from Faraday's first law of electrolysis. But you have to know that I told you before, when I started solving this, that in this question, what lacking is the electrochemical equivalent. So here, we may start finding the electrochemical equivalent of copper. After getting the electrochemical equivalent, we will be in the position of using the formula from Faraday's first law directly without any problem. Now, let us first of all finding the electrochemical equivalent, the electrochemical equivalent of copper. Now, I think you remember, we have said that to get the electrochemical equivalent is equal to relative atomic mass over the product of valence and the Faraday's constant. I think you remember. Now let us see now what element are we dealing with? We are dealing with the copper. Now, the relative atomic mass of copper is how much? We are given that it is 63.5. Now, if it is 63.5, it must put in part of numerator 63.5 over. We are going to divide with the valence of copper. Copper is a valence of 2. So we put 2 here times Faraday's constant. Faraday's constant is equal to 96,500 coulombs. So it is 96,500. Here, now let us divide so as to get the electrochemical equivalent of copper. Let us use a calculator to compute that mathematical term. We have 63.5 over 2 times 96,500. The answer which we get here is 3.290 times 10 raised to negative 4. 10 raised to negative 4. This is the electrochemical equivalent of copper. Now, what is the unit? I told you that the unit for electrochemical equivalent is gram per coulomb. So, the electrochemical equivalent of copper is 3.290 times 10 raised to negative 4 gram per coulomb. Now, after that, let us solve directly by using the equation obtained when the Faraday's first law of electrolysis is applied. The equation is that we are told that to get mass from Faraday's first law of electrolysis, mass is direct proportion to the quantity of electricity passed through the electrolyte. Now, mass is equal to Z, which is electrochemical equivalent, times current times time. This is the equation according to Faraday's first law of electrolysis. Now, let us substitute the value of Z, I, and T so as to get the mass. Here, we have obtained that the electrochemical equivalent of copper is 3.290 times 10 raised to negative 4. 10 raised to negative 4 times current. Current we are given is 3.2 ampere times time. Time we are given is 30 minutes, which is equivalent to 1,800 seconds. 1,800 seconds. Now, what do we get? Let us compute in a calculator. We have 3.2 times 3.290 times 10 raised to negative 4 times 3.2 times 1,800. What do we get? We get 1.89504. This you have to know is in terms of grams, so this can be approximated as 1.90 gram of copper. So you can find that the values obtained in the alternative and in the first solution we have made are equal. So we say that we conclude by saying that the mass of copper deposited at the cathode will be 1.90 gram. Yes, that is the way we carry out various calculations concerning with the Faraday's first law of electrolysis. I hope you have understood well the way we use the two methods, the two ways of calculating various problems concerning with the Faraday's first law of electrolysis. One technique we use is to use a balanced chemical equation, and the second is to use direct formula from Faraday's first law of electrolysis. Now this was the second example. Let us see a third example.